So I'm going to talk about, let's say, overview of supervised methods in machine learning, and this is a part of your TechWhip course that is ongoing. My name is Animesh. I'm in the electrical engineering department here. Subsequently, if you have any questions, feel free to send a question by email. The contact would generally be available on my web page. All right. So the scope of machine learning is quite vast now. The developments in machine learning have gone on for past 70, 80 years, and so therefore it's a grave injustice to some extent to kind of imagine that one can capture it in a couple of hours. So we only have a 3-hour session, but nonetheless, for that reason, what I am doing is I'm focusing only on supervised methods, and there also we'll try to kind of scratch the surface of it, or maybe the techniques that are necessary, or the mathematical tools that are necessary for learning, for understanding machine learning. All right, so these are the topics that I'll be covering. So we'll be starting with some basics of machine learning, just how to kind of spot a machine learning problem, and then we'll be discussing some machine learning examples leading us to supervised learning. And then in supervised classification methods, I'll be talking about a few known ones: LDA, QDA, SVM, support vector machine, or PCA, which is called principal component analysis. And I may give you some hints on how to do regression if you're not into classification, but let's say regression or estimation style of problems. And then finally, we'll conclude. All right, so let's start with machine learning basics. So a machine learning program, or machine learning is often called as ML nowadays. So I'm not spending, we have lost some time, so I'm not, let's say I'm not glorifying machine learning to you right now, but in a nutshell, this is one of the most happening technology areas as we speak, and that has been true for past 7 to 8 years. And so a machine learning program typically consists of what we call as a task T. So there would be some task that we wish the machine to perform. I'll give you a concrete example in the next couple of slides. There's some performance measure P which is associated with the output of the machine. So whenever the machine performs the task T, it will kind of come along with a quantifiable measure of performance that we are calling as P. And there's this notion of experience. So the experience meaning the setup in which the whole problem of this task and this performance measure is cast, that is called as an experience E. All right. So for example, the task can be a classification task, like for example, classify bits into 0 and 1, or classify digits into 0, 1, 2, all the way up to 9. Something that we do, for example, in handwritten digit recognition. P is the performance measure, so one can just measure, let's say, the error rate on some sort of test data set, or let's say one can look at mean squared error when we are doing regression and so on. And this experience can be supervised, unsupervised, and this list has been increasing. So people have what is called as reinforcement learning. I think you may have heard the term, or self-supervised learning, and so on. So that's what we mean by experience. All right. So the way machine learning. So if you think about it, machine learning is so there's this notion of a task that has to be performed, and this task is inherently statistical in nature. So then one might kind of ask the question, how is it different from classical statistics, right? So for example, in classical statistics, given population data, one may be interested in finding the population mean, right? And that very much sounds like a prediction task. You want to predict the population mean, and something that statisticians have been doing for a while. So how does it differ from classical statistics? So the key idea here is it's data driven, which means that typically when we study statistics or probability and statistics, you always start with a probability model. You always assume that, let's say, the underlying distribution is Gaussian or gamma or exponential or Poisson, or some such assumption is made, and after that we kind of do inference on top of it. In machine learning, it's not done like that. It's a data driven technique, which means you start with no model, right? So all that you assume is that the data samples are independent, or let's say independent and identically distributed, and after that you want to perform the task T. So if you look at machine learning right now, the data driven statistical techniques data driven meaning, not much assumption is made about the distribution of the statistical or probabilistic data to begin with. So you don't assume Gaussianity, you don't assume that variable is Poisson, no such assumption is made. And so that's where it starts. So it's a data driven statistical technique, and this would be at the heart of any contemporary machine learning program. So for example, you may have heard of PCA or principal component analysis. When people do principal component analysis, they don't assume that the variable is of a certain distribution, they just cannot do PCA. So once again, data driven implies that probability model, meaning assumption about the distribution of the underlying statistical variables. So that is either unavailable, so you make very relaxed assumption that the distribution is not available at all, or in some settings one may assume that it's partly available, so you know it but not fully. Even if the distribution is assumed to be known, typically parameters of the distributions are assumed to be not known, which is often leads to what is called as let's say parameter tuning or hyperparameter tuning and so on. All right. So one aspect of statistical learning is to show that a data-driven statistical method, meaning a method or a predictor or a machine learning program that works directly on the data, that's performing some task T, is going to, let's say, converge or meaning like agree with its underlying true value. So when you are predicting, let's say, handwritten digits into the corresponding, the numerical output 0, 1, 2 all the way up to 9, then you want the output to agree with what was written on the paper in the first place. So let me give you an example so that these things become a little bit more concrete. So there's this data set called MNIST, all right, and so it's a handwritten digit recognition problem which was posed back in somewhere around 1990 by Jan LeCun, and so it's a very simple data set to kind of begin experimentation, but nonetheless it's a slightly it's just complicated enough to kind of highlight all the difficulties that one might face while working with machine learning programs. So what does it consist of? So there's this notion of training images, so that I'll tell you in maybe the next slide, and it has some 10,000 test images. So 60,000 is like moderately large number, not very small, not very large. And what does it consist of? So it consists of images. These are digital images, so they would typically be pixelated, and so the size of these images is 28 pixel by 28 pixel, meaning so if I look at, let's say, this handwritten digit 0 here, this is on the top left, then this is basically corresponding to a 28 pixel wide and a 28 pixel tall image here. All the zeros that you see, they all are 28 pixel wide and 28 pixel tall. The same is true for 1, the same is true for 2, and so on. So you may wonder, like, where did this data set came from? So well, that was curated by early machine learning researchers, primarily, I believe, led by Jan LeCun. All right. So, and that data set is kind of often called, it's canonically called as MNIST database, and this problem is called as handwritten digit recognition. So the whole idea, like, these digits were at some point written by people by hand, and all this has to be classified. So the whole idea is, like, if I take these images and feed it onto a machine learning program, it should be able to tell which digit is it reading. Now it seems like an easy task because this 0 looks very different than this 1 and so on, but the boundaries can be quite blurry. Like, for example, if you look at this 7, do you think of this as a 7 or do you think of this as a 1? Or similarly, if you see this 8, is it an 8 or is it a 0? So it's true that most of the digits look like what they should be, but then there are some digits which are like kind of hard to figure out. Like, for example, is this a 7 or a 4? And by the way, this is only like a few examples. So just imagine what would happen across 60,000 such images. Okay. All right. So what is the type of classification here? So what's the task at hand? The task is classification of images which are 28 pixel by 28 pixel into digits. So that's the task that is there for the machine learning program, right? How do I measure, the performance? So there's something called as a confusion matrix. A slightly simpler way to understand confusion matrix is how many zeros, let's say, get misclassified by the my machine learning program into, let's say, 1, 2, and so on. So that's basically confusion matrix. So ideally you want the confusion matrix to be nearly diagonal, like, so all the zeros should get classified to 0, all the ones should get classified to 1, and so on. So you want the typically on the diagonal you will have like you want the confusion matrix to look almost diagonal. And here E is called as supervised learning, and the reason for that is, there's this notion of a training image and a test image. So the way training images work is that each of these images corresponding to 0, they come along with a label which says that this particular image is a 0. So while the machine learning program is training on these images, it knows that which images correspond to 0, which images correspond to 1. So even though this 7 looks like a 1, the program is still kind of told that, look, even though it looks like a 1 to you, it's still a 7, so that you can adjust your predictor accordingly and so on. All right, so that's why it's called as a supervised learning, in a sense that you are helping or you're supervising the learning process of the machine learning program. All right, so what is the goal of digit recognition then? So you want to come up with a decision maker, right? So this D here is a decision maker. The decision maker takes an image such as this, which is 28 by 28 pixel, and it gives an output which is a digit. So that's the task. And then you can measure again performance by what I called as confusion matrix earlier, but you can even think of that as basically just classification accuracy. How many zeros were kind of confused into some other digit? How many ones were confused into some other digit? So that becomes a performance measure. So this is one example of supervised learning where we are doing a classification task. Let me give you an example of a regression task. Something that we will not touch upon too much in this 3 hours, but nonetheless, I think it's probably a good idea to see more than one type of machine learning program. All right, so often we want to learn dependencies between variables, which are through calculus and all. I mean, we call them as functions. So let us say there's this, there's this underlying red graph, which happens to be actually a cubic polynomial, and this is what has to be learned, and that's what is shown in red here. So fx is the underlying function that I wish to learn. Okay, so that's some dependency which is, let's say, output of my statistical experiment, and I wish to understand it better. And so the x-axis is limited to 0 to 1, so that's the interval in which we are observing the function. Typically, most finite experiments would involve a finite support region, so that's not too bad. But what kind of spoils this learning experience is that there is measurement noise. So that's indicated by this fx plus wx. So wx here is the kind of noise process which is going to affect the sample measurements. All right, so ideally I should have seen these red dots, but because of measurement noise, I don't end up seeing these red dots. I kind of get to see these scattered blue dots, right? And they are kind of like everywhere. All right, so here the task is learning of function which is depicted in red. So I want to learn this cubic dependency. There's a mild cubic dependency, as you can see, right? It almost looks like a straight line, maybe with slight bulge on both sides. It's a mild cubic dependency that I want to learn. And so that's the task that I'm kind of interested in while I'm kind of solving this machine learning program. How do I measure P or the performance? So well, one way would be the classical method, which is just looking at the mean squared error. So if instead of f of x, I come up with like a predictor, if I come up with a predictor of f of x, then I can just look at the mean squared error between fx and its predictor in this interval. I can also look at, let's say, the largest error between them, or I can even look at the so-called absolute error, which kind of sounds like the median between them. And here experience is basically its regression or estimation, and still supervised because for every point x, so the value of x is kind of given, right? So the value of x is given, and then you are trying to figure out, so the value of x as well as the noisy sample that is available, both are given, right? So this is basically a classical regression problem If the distribution of noise W was given, then it becomes an estimation problem, which again goes back to classical probability and statistics. So the key difference here is that the distribution of W may not be available. One may only know that it's zero mean and independent, but we don't know anything more than that. How would you kind of solve this problem then? All right. And so it kind of looks like an easy task, but I'll just give you some hints into why these kind of problems are non-trivial. Okay, just so that it doesn't look too easy. And it's easy in the sense that people know how to solve it, but it's not easy in the sense that it took a while for people to get to the current state of the art of solution. Okay, so these tasks become kind of non-obvious when measurement noise is present, as we discussed in the previous slide also. And if I just kind of like look at some sort of trend line, right? If you present this to someone who is not very well versed in statistics and so on, they will say that, look, it almost looks like kind of descending, right? So maybe I can just fit a straight line. That's the first guess that anyone can make. But the problem with that is you will lose out on this cubic dependence. So the cubic dependence is mild, but nonetheless, if you want the function accurately, then you have to capture it. And that becomes very, very non-obvious. This is even worse if, for example, if the noise distribution was like having a higher variance. So here we are having the same function. So you may say like, no, this looks like a different function. So what exactly is going on? So when the noise becomes larger, you would see that the dynamic range here, which is the dynamic range of the function value. So here it's from minus 0.25 to plus 0.25. This is from minus 2 to plus 2. All right, so the noise is larger. Even though this is cubic, you kind of end up seeing it almost as a straight line. So if you just kind of like gaze at the data and try to make a prediction, there's a good chance that you would fail. So for example, if you see all this scattered data here, right, you will end up believing that it's almost zero, right, because there is no trend. And it's instructive, right? You kind of mask this red plot here and show it to a person and ask like, do you see a trend? And they would be like, no, I don't see a trend. Probably it's all around, kind of centered around zero, right? But it's not true. There's some mild variation, and that has to be captured. All right, so if I had more time, beyond these 3 hours, we would have done some of this, but let's get back to supervised learning. So one reason that I'll be focusing on MNIST again and again, like I said, it's a complicated enough data set in the sense that it has 60,000 training samples, which is not too large, not too small, and it's supervised, so you kind of know how to begin thinking about machine learning problems. As you can guess, unsupervised learnings are unsupervised or other kind of learning problems are harder. So it turned out that among all the machine learning programs, supervised was the first one to show up. And you'd be surprised, when did it show up? So the first supervised learning program that we kind of understand or know of today it dates back to as early as 1936. So it was even before probability was formally defined. It was done by one of the visionaries. I think you may have heard the name of Fisher. It comes from Fisher's experiment on what we now call as iris data set. All right. So supervised learning is kind of like cool to begin with. Just think of it like that. And so the core advantage of MNIST is even though it's not very voluminous, it's voluminous enough to give you statistical trends, but it's not voluminous enough to kind of make your machine learning program lag. So your hardware will be adept at adjusting to MNIST data set, because these images are small, right? 28 pixel by 28 pixel. Anyone has heard of any newer data set that people experiment upon? So you may have heard of, I don't know, at least through some talk or discussion, maybe something that is called as an ImageNet data set or a CIFAR10 data set and so on. So those are larger images, and those are harder to accumulate and assimilate because they are voluminous. They are not 28 by 28 pixels, they are much larger. Typically they run into hundreds of pixels by hundreds of pixels, and they are in color. So this this MNIST data set is in black and white. The moment you add color, you already have like 3 or 4 times more number of pixels corresponding to each color that an image can have. So those images are harder to kind of deal with. So much so that if you have any cool idea in machine learning program, let's say related to either supervised or unsupervised experience, it's kind of instructive to start with MNIST. The data set is freely available, and a lot of standard packages are there which will help you to kind of begin experimenting with it right away. And again, so much so that it's often called as a Drosophila. You understand what Drosophila means? So Drosophila is like, the first complicated enough or the standard experiment that you would want to do with a machine learning program. So it's often kind of dubbed as that. All right. So you may kind of also question, like, while we, yes.
Is there any minimum limit on the size of the training database? Like, is something where we say, is it sufficient enough for the learning process?
So that's a good question. So for example, in this setup, we can ask, like, what's the minimum number of samples that I need to be able to get the red graph exactly right? And the answer to that would be infinite, right? Because there is noise, so no matter how many samples you collect, you will always have some mean squared error. The mean squared error would never be 0. Similarly, for this digit recognition problem also, the misclassification probability, or let's say the number of misclassified entries, they may never become 0, no matter how hard you train or no matter how many training samples.
I was asking the reverse. As an example, as I understand you, this particular thing, you had 6,000 samples like this, 6,000 columns, because 60,000 images. So instead of using 6,000 columns, suppose I had only 2,000 columns available with me.
Understand your
Would
question.
the classification be more accurate or less accurate? Would
So
it have
as
some
you can
impact?
imagine, with lesser samples, the program will be able to learn a little bit less, and so therefore you would expect the the classification accuracy to deteriorate as the number of samples is reduced. And one of the key things that people explore is this trade-off: how many samples do I need so that the classification accuracy, it will never become perfect, but it's near perfect. All right. So that's something.
Would there be a learning as you classify? I mean, you've got the training done. Now you're doing the classification, and while
I think so.
classification,
So that's called as active learning or online learning. But if you just look at supervised learning, then new samples. I mean, so once you build the predictor, you kind of don't touch it. But if you are kind of adapting the predictor or the machine learning program while the classification is going on, then basically, yeah, that's a different experience. That's not supervised learning. That would correspond to, let's say, online learning or active learning, meaning the program kind of learns as it keeps on classifying more and more data. But that's a very good question. So in a nutshell again, so one thing one might ask is, how does the mean squared error reduce as I add more and more training samples? So that was the question that we were having. Can I get, or in other words, how many training samples are good enough to get within a certain target accuracy that you may have, right? And that accuracy may come from mean squared error or absolute error or whatever that you are kind of interested in. So, so to be able to answer those, you would need some good solid handle or grasp on the statistical learning part of machine learning, because there you would begin with, let's say, so you would kind of argue that, let's say, the noise samples are independent. So after that, you can bring in things like law of large numbers and all to explain what is the number of training samples do I need for, let's say, getting the target accuracy within some limit. And you would like to do all that within that same data-driven paradigm that I was talking about. So you don't want to make too much assumption about the model of the noise. Similarly, for example, if you see here, I mean, one may kind of say that, look, I'll come up with a model for the digit 0, I'll come up with a model for the digit 1, and so on. But those efforts did not succeed grandly. And one reason was that typically, if you look at real life data sets, it's very hard to come up with a model for that. So, I mean, these are just handwritten digits. You can imagine that if you're looking at ImageNet or CPAR10 kind of data set, it's very difficult to come up with a model for the data set itself. And for that reason, machine learning has been slowly evolving into more like let's say, a computational engineering or it's kind of less grounded in assuming a model. I mean, the core assumption that we typically make is that the like if there is noise, then the noise is independent. If there is data, then it's an independent realization of what I am seeing, and so on. So those are the only assumptions that we make. All right. So when is supervised learning used? So if we have access to training samples, if someone is there to come up with these class labels. So what is a class here? Class, for example, is the digit output, right? So there are 9 classes here: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8 and 9 are not shown here, but you can imagine they would also be there. So those are the 10 classes when it corresponds to digit. If you're classifying, for example, alphabet, then there would be 26 classes, all the way from A to Z. All right. So those are the class labels, and then some test samples are given, so that once you build your predictor, you apply your predictor on the test samples to see whether it is doing its job properly or not. So when would you use it? So whenever training data is available, right? So if you have, let's say, experimental resources to collect enough or sufficient training data, then it may help you in building a predictor. And then, I mean, we have seen one example already that was of the MNIST dataset, where labeled images are available to tune or design a machine learning predictor. So the other examples are they are these so-called histopathological images. So these correspond to disease-related pathology slides, and here there would be trained pathologists who can label various pathology images. For example, whether there is a tumor or there is no tumor, if there is a gland enlargement or there is no gland enlargement. I mean, those kind of things can be labeled, and then one can again come up with a predictor so that the machine learning program can just look at the histopathological image output and predict whether there is a tumor or no tumor, even when the human is not there. So that's like automatic prediction. It's not automatic in the sense that there is a machine learning program which is doing it. Or, for example, one may have a smart building or a smart room. I mean, that's what people call it as. I would just call it as a room or a building. So it's often called as indoor climatology. Climatology because you want to understand the climate within a room. And so, for example, this is a large room. There are few cooling sources. I mean, there are actually quite a few in this class. For example, all these vents that you see, these are AC vents. Where the number of vents is smaller, then the temperature gradient that we get in a room is typically not uniform. So, different parts of the room will have different temperature, and different users will therefore have different comfort level, even though they are present in the same room, depending on where you are sitting. If you're just below the AC duct, you would feel a bit colder. If you are kind of there in the corner where there is very little air circulation, then you will have like reduced comfort level. So one way I want to, for example, predict what would be the comfort level of users given so many AC vents that I can have, and maybe one can even regulate the speed of the AC fan, as well as one can even regulate, let's say, the temperature at which each AC duct kind of pumps the air, and so on. So all these are examples of supervised learning. So you kind of initialize it in enough number of states, and then you will have some output, and after that you build a predictor. So then you may say, like, this seems like the most natural thing to do, but will I ever have a setup where I would like unsupervised learning? And any guesses when will you use it? Well, whenever labeling the data, whenever kind of labeling those images or labeling those functions is too expensive or too large or just too uncertain to be labeled, then you would not like to use a supervised learning setup. You would like to use what is called as unsupervised learning. And I'll just give you an example. So here training samples are given. So you still have access, your program will still have access to training samples, but they will be without any class label. So that's basically the same as MNIST or handwritten digit problem, except let's say if the digit labels 0 to 9 were not there, then it becomes an unsupervised learning problem. And there, one of the way people approach it is by clustering it. All right. So what you will do is you will just kind of cluster similar looking or training points which kind of appear to be similar together. Yes.
one, you're seeing that example, movies you may like.
I'll get there. Yeah.
Even in this case, I think the movies would still be initially labeled, right? I mean,
No, no, I'll get there. Just let me finish. Maybe you can return to your question. So let's look at example where it's when labeling the data is either too expensive or too large or even uncertain. All right. So if you use Google News or any other news aggregator that you have, you would notice that below every news article it would have this idea that related news, right? And typically they do it by plethora of techniques. I mean, there's no single technique that is there. The most common and obvious one is what is called as a bag of words technique. So each news article, because it's a text file, so it can be scanned by Google's server, and then all the infrequent but important words can be kind of noted, right? So for example, prepositions like is, this, was, all those things can be ignored. But if you see so for example, if it says Donald Trump visit or India and so on, so you can kind of start collecting keywords like that. And if enough keywords match between two different news articles, then you would kind of begin to classify it as related. All right, so here it is too expensive for a person to kind of sit down and label each news article, because then Google will have to pay them heavily, and the person will take a lot of time to be able to classify a news article whether two articles are similar or not. Then they may also make error. So it's not only too expensive, it's probably prone to error as well if humans are involved in there. All right. Now, if you see a site like Amazon.com or Amazon.in as far as India goes, then you would be shown things like products you may like. And even though Amazon feels that these are products you may like, Amazon has no way to know whether you would like those products or not. So Amazon doesn't have the ground truth. So that's uncertain. All right. So no matter how strongly Amazon feels that you're going to buy this product or like this product, there is no way Amazon would know it before you actually try, buy and try the product. And even then, if you don't leave a review, again, then Amazon would not know whether you like that particular product or not. So there is just too much uncertainty here. So in this kind of setup, again, it's not possible to do supervised learning here. Then this is the third example that I have where I'm kind of talking about too large data sets to be labeled. So Netflix, as you may be aware, I think last year it was still catching up. So bulk of the crowd was unaware of this, but by now I think Netflix, Hotstar, and Amazon Prime, these are quite popular among at least tech-savvy users. So they would typically show you something like, based on what you have seen, the movies that you may like. And here I would say there is too large a set to be labeled. So the number of movies would typically be, let's say, between 1,000 to 10,000, somewhere around in that number. And the number of users in Netflix, any guesses what's the number of users that are there in Netflix? Millions? Easily, right? Millions actually are there probably only in California. No, not trillion. There are not that many humans on the earth, luckily. So not in trillions. Unless someone is buying lots of accounts without using them. So it's kind of safe to assume maybe somewhere between maybe 100 million to a billion, right? If you assume 20% penetration on the entire earth and so on. All right, so that's a very large set, right? And every user is not seeing all the movies, right? This is not possible, both because of time constraint and other issues like bandwidth and so on. Even if one has time, one may not have bandwidth. If you have time and bandwidth both, then after that also you would not go back and rate. So that issue, this uncertainty is still kind of here. Even if you see a Netflix movie, you may not go back and rate it. So then Netflix would still kind of remain in the dark. So this is just too large a set to be labeled. So even if you wanted to label it, even then you could kind of not finish doing this. All right. So all this kind of sounds cool. So what we'll do next is I'll spend some time on supervised learning, because that's the kind of the starting problem in machine learning. And as you would have noted that we are looking at digits, we are talking about statistical predictor and so on. So the classical route towards understanding all that is through linear algebra, through optimization, and through basic statistics. So what we'll do is we'll start with linear algebra. We'll not do optimization again because of time constraints, and so what we'll do is we will understand these classical supervised learning methods which don't involve optimization. All right. So let me kind of get started on the linear algebra review part. This is supposed to be kind of like, I'm guessing you would have seen it at some point through your career. It's just kind of to quickly, what do you call, refresh your understanding of it. All right. Okay. So here, so the first thing that you would typically start off with in a linear algebra course is things like vector spaces, fields, and so on. I'm skipping that. I'm assuming that you know what a vector means. I am assuming you know what a real number means, which comes from a real field, and so on. So we'll start with this idea of linear combinations and span right away. So if a set of vectors v1 to vn, so n here is some arbitrary number, but if these vectors are given, then a linear combination is defined. A linear combination is defined as a vector of this type. So what you do is you take the first vector, multiply it with a scalar, take second vector, multiply it with some other scalar, and so there are n different scalars which are involved, and n different vectors which are kind of involved here, and so you sum it all up. That will give you a resultant vector. That's called as a linear combination. All right. And so the whole idea is that you want to think of a1, a2, an as some sort of independent scalars which you want to move around or change around, and v1 to vn are something like a fixed set of vectors. So that leads us to this idea of span. So for the same set of vectors v1 to vn, their span is basically the all possible linear combinations that you can obtain, right? So this is one possible linear combination, a1, a2, and so on, maybe some fixed numbers. So the way you obtain span is by you start changing, the values of a1, a2, an in the set of reals. So you change, and that may mean basically, you are going to get an infinite number of vectors. Truly so. I mean, so typically a span would always be infinite, having an infinite number of elements. But nonetheless, it has, even though it has infinite number of elements, it still has the structure that the span of these vectors v1 to vn is always going to be a linear combination of these vectors v1 to vn. All right. So they would always. So this is basically the way to read this is the span is the set of all v vectors such that v vector is linear combination of v1 to vn for some a1 to an. All right. Now zero vector will always be in a span because I can select a1, a2 all the way up to an to be all 0. So therefore span always includes zero vector. The other thing that we know is that span is a subspace of Rm. Rm meaning m-dimensional real numbers where each vector Vn is also in Rm. So to be able to add these vectors V1 to Vn, we would require that they are having the same dimension, right? If one vector is one dimensional, the other is two dimensional, you cannot possibly add them. So we are assuming that all the vectors are in the m-dimensional space of reals, and therefore we can kind of add them. All right. So let me give you some brief examples of span. So this is just a single vector, and if we look at all possible linear combinations, then we are just going to take the vector and multiply it by a scalar, right? And if I vary the scalar in the entire real line, then I'll get this as the span of this particular vector. So this is the vector, and this whole line kind of extending both ways towards plus and minus infinity, that's the span. If I start with two vectors, and if I take all possible linear combinations, I'll end up with this plane, so that becomes the span. So let's try and understand maybe a digital image, such as what we saw in the MNIST dataset as a linear span. So this is slightly scaled down. So instead of 28 pixel by 28 pixel, I kind of scaled it down to 14 pixel by 14 pixel just so that I can represent it easily. And this looks like approximately like a digit 0, and that's what it is. In fact, it's the first image of 0 in the MNIST dataset, and that has been further kind of shrunk down to 14 by 14 pixel. So one way to represent this is as follows. So you would say that this is the third row and the seventh column where I kind of see the first non-zero entry, and that's 29. The second non-zero entry is at, this x equal to 3, sorry, the third row and the 8th column, and there I kind of see this value 258, the third row and 9th column. I mean, it's not visible, right? It almost looks like black. It's not black. It's nearly black. If it was 0, it would be nearly black, but it's actually 32. So the images or the image pixels range between 0 to 255. So if you see like something which is bright, you kind of see something around 253 or 252 and so on. On the other hand, what looks dark is around, let's say, whatever, 30 or sometimes the neutral gray like 146 and so on. And all other pixels which are exactly black are just 0. So this is one way in which you can represent an image, right? So for each pixel, we are saying that, this is the these are the values. So the question is, can I represent this as a linear span? And the answer is yes. So what are the basis vectors or the vectors that we are kind of looking at when we are talking about linear combination? So imagine these kind of vectors. So V1, which is the first vector, and that's basically it's a vector operating on 2 dimensions. So the vector V1 is 1 if the first pixel or if the first row and the first column of the pixel are equal to 1, otherwise it is 0. Similarly, V2 vector is 1 if the if I, which is the if it's second row and the and if it's the first column and so on and so on. So you can keep constructing these kind of images. So basically these are images which are equal to 1 or equal to 255 exactly at 1 pixel and 0 otherwise. So if I take this kind of basis, then I can start representing images like these using a linear combination by using these kind of coefficients. So these basically represent the AIs that we had in the definition of in the definition of linear combination, and these are the vectors that we were talking about. Okay.
The vectors that you just wrote down, V1 in the previous slide,
Yes.
VI, V1, V2. So these are representing each of the pixel. I mean,
So I and J here are the pixel indices. So I will go from, let's say, 1 to 14.
Correct.
J will also go from 1 to 14.
But then what does V1 represent?
So V1 is the first vector, and V1 vector is such that it's only non-zero in the first pixel on the top left corner. Similarly, V2 is the vector which is having one non-zero pixel, only one non-zero pixel, and that's, let's say, at the second row and the first column. Similarly, V3 is again one non-zero vector which is having only one non-zero pixel at third row and first column and so on. So you can construct. So how many such vectors will you be able to construct? So it's going to construct 14 by 14, so 196 number of such vectors. Once you have constructed them, then you can represent any image such as this by, so what you would do is you would say that my image X is 29 times the, so you'll have to do 3 times 14 plus 7. So you will have to take V49 and multiply it by 29. And in that manner, you will be able to represent this image as a linear combination of these constituent single pixel images or single non-zero pixel images. Okay, and this is one way to understand how linear algebra will, let's say, creep into a machine learning problem, because linear algebra helps us in understanding any image or any vector as a set of constituent vectors or as a combination of constituent vectors. So that's where machine learning, that's where linear algebra is useful. In fact, it's kind of useful through engineering, right? Anywhere we want to kind of understand a function or a vector as a linear combination of constituent vectors, I think at that point linear algebra becomes useful. So there's this also notion of basis or dimension that kind of creeps in, not creeps in, it's kind of brought into linear algebra. So there's this notion of smallest set of vectors V1 to Vn such that any element V in a vector space can be expressed as a linear combination of these constituent vectors V1 to Vn. All right. So this kind of set is called as a basis for the vector space V. And you would think of this A1 to An as the coordinates of the vector v in this particular basis. So there are three things that kind of show up here. One is that there's a vector space v or a linear space v that's kind of shown here, and then there's this smallest set of vectors v1 to vn, which are used to represent any vector in v as a linear combination of v1 to vn. Okay. Now it turns out that the dimension of vector space v will therefore become n, which is basically the number of elements that are there in the basis set. And but the basis is not unique, so you can have more than one basis. But if I fix the basis, then the coordinates are unique. Okay. So while the coordinates are not, while the basis is not fixed, the coordinates are to some extent flexible. But the moment the coordinates are, the basis is fixed, then the coordinates have to become unique. So that again comes from basic linear algebra, and that's actually happening because the basis is basically a smallest set of vectors. So that's where the underlying property is. All right. So let's look at, let's say, a vector space, three-dimensional vector space. So this is 3 axis, and it's of dimension 3 as we know of. Then I can have a two-dimensional subspace of it, and that's kind of shown by this plane that is drawn here. Here the vectors are spanning in the x and the y direction, not in this z direction here. All right, so this is a vector space. So this is a three-dimensional vector space, and this is its subspace. However, if I kind of carve a plane like this, but it's not crossing through 0. So this one is crossing through 0. If I kind of carve it out or make it so that it does not cross through 0, then I will not get a subspace. In fact, it's called as an affine space or affine subspace by some. I mean, it's not correct to call it as subspace, but often it's called as an affine set or affine subset. So that also you may be able to get. So I need to take 2 minutes of break. I think I'll be back.